What exactly is gravity? In 1687, in his work, Mathematical Principles of Natural Philosophy, Newton introduced the law of universal gravitation, stating that all objects in the universe have mass and that there is always a gravitational force between two objects. Every mass attracts every other mass, and this gravitational force is inversely proportional to the square of the distance between the two objects. This means that if the distance doubles, the force will decrease by 4 times, and if the distance triples, the force will decrease by 9 times. This is how Newton explained gravity. However, Newton himself doubted his theory. In a letter to a friend, he wrote that one object being able to affect another at a great distance through a vacuum without any intermediary was such an absurdity that he believed no one with a basic understanding of philosophy could accept it. Let's imagine if you kick a ball, the physical contact between your foot and the ball causes the ball to move. But what about the Sun and the Earth, with an average distance of 150 million kilometers between them? In this case, scientists have always been puzzled about the type of force that could create such a connection between objects, and that's when Albert Einstein spoke up, pointing out that gravity is not a force but merely a consequence of the curvature of space-time. One day, while Einstein was sitting in his office, he saw a man cleaning the window of a nearby building. He began to imagine what would happen if the man fell. Let's skip the scenario of the man hitting the ground and focus instead on what the brilliant physicist of the 20th century was thinking at that moment. During free fall, the only force acting on the man is gravity. If he were inside an elevator, he wouldn't be able to tell if he was falling because there would be no point of reference. This means that there is no difference between a person in free fall and one floating in space because, in both cases, they wouldn't feel any gravity. To clarify further, now the man is floating inside an elevator in outer space with a ball beside him. At this point, a motor beneath the elevator starts up, giving it an acceleration of 9.8 meters per second squared, equal to the gravitational acceleration of Earth. Instantly, the ball and the man would fall to the floor of the elevator. What can be done with the help of gravity on Earth can also be done in this moving elevator. The man wouldn't notice any difference whether he's in space or on Earth. Thus, free fall on Earth is equivalent to free movement in space. The gravity on Earth is equivalent to an acceleration of 9.8 meters per second squared in space. This means that acceleration causes gravity, or in some way, gravity and acceleration are just different ways of describing the same thing. Now let's turn off the motor. The elevator will start to float in space, and so will the man and the ball. But what would happen if the man threw the ball in a straight line? Of course, it would travel in a straight line. What if the elevator were accelerating? Surely, you could guess that the ball would move downward in a curved path and hit the elevator floor. Now replace the ball with a beam of light. How would the light travel in an accelerating elevator? Would it curve? Einstein's answer was yes. If you had a precise measuring device, you could measure the height of the light beam and find that the height at the opposite side would be slightly lower than at the source. Why is that? Because while the light is traveling across the elevator, the floor of the elevator is moving upward with an acceleration of 9.8 meters per second squared, making the light beam appear to curve downward. However, if you're on Earth and measure the two heights, you might think there should be no difference. The light should travel straight across the room. While this seems reasonable, Einstein argued that this can't happen because it would violate the principle of equivalence. The elevator accelerating at 9.8 meters per second squared in space should not be different from a room on the ground. In other words, light must bend when in a gravitational field. Einstein then imagined the curved surface of the Earth. If you were to walk straight from a location to the North Pole, you might think you're walking in a straight line. But to an outside observer, you're actually following a curved path. Similarly, light always moves in a straight line, but because the space it travels through is curved, the light also bends. In space, where there is mass and energy, space becomes curved in a certain way, causing the shortest path that light can take to be a curved one. This is the foundation of Einstein's general theory of relativity. His theory suggests that gravity is not a force between massive objects, but rather a force arising from the interaction between those objects and space itself. Later, American theoretical physicist John Wheeler, one of Einstein's last collaborators, summarized this theory in a simple sentence. Space-time tells matter how to move, and matter tells space-time how to curve. Yes, general relativity is simply that. You can imagine the space in the universe as a trampoline. This trampoline, combined with the fourth dimension, time, forms space-time. Suppose on this trampoline there are a heavy man and a light man. It's easy to see that the trampoline will curve at the position of the heavy man, causing the light man to be pulled toward him, even though they are not directly interacting with each other. Similarly, when the sun curves space-time, Earth is drawn toward it. In short, it's not a force, but rather the result of the curved space affecting the objects on that curve. Now you may wonder, if the space beneath an object with mass is curved, what about the space above it? We should note that the comparison of space-time to a trampoline, which you often see in many videos, is really a two-dimensional image meant to help visualize the interaction. In reality, the interaction happens in 3D space like this model. Because this model is difficult to animate and also challenging for people to imagine, it's less commonly used, but it's certainly more accurate. When the theory of general relativity was published in 1915, many scientists still doubted Einstein's theory, as there was no real-world evidence to confirm it. It wasn't until 4 years later, in 1919, that an expedition led by British astronomer Arthur Eddington tested the theory. At that time, they knew the precise positions of some stars near the sun. If Einstein's theory were correct, then the light from those stars would bend due to the curved space near the sun, and their observed positions would differ slightly from the calculated ones. And that's exactly what they observed during the total solar eclipse on May 29, 1919. After this event, Albert Einstein became one of the greatest scientists of all time. His general theory of relativity, also known as the theory of gravitation, not only simplifies the understanding of gravity, but also shows the world how the universe works. But there's still one problem we haven't clarified. Why is there time? How does time manifest within the structure of space-time, and how does its dilation occur? The relationship between space and time is covered in the special theory of relativity, which we will explore in the next video.